I want to start today's deep dive by asking you to do something that, well, it feels a bit cliche, but stick with me for a second. I want you to picture a creative brain.
Okay.
If you close your eyes and really imagine the biological machinery inside the head of a Mozart or a Frida Kahlo or a Steve Jobs, what do you actually see?
I think for most people, the image is pretty standard. It's
Yeah.
it's glowing, right? It's vibrant.
Totally.
There's this idea of a light bulb going off. It's all about more energy, more neurons firing, more activity. It's like a fireworks display inside the skull.
Exactly. And if you walked out onto the street right now and you asked 10 people where creativity comes from, I bet 9 of them would tap the right side of their head.
The old right brain myth.
It is the absolute zombie of neuroscience. It just will not die.
It's so stubborn.
You see it everywhere. In corporate training manuals, in those self-help books. Unlock your right brain to be more creative. Tap into your inner artist by ignoring your logical left brain.
And, it's rooted in a tiny grain of truth. There are hemispheric differences, of course. But as a map for something as complex as creativity, it's just woefully inadequate.
It's like saying a car drives fast because of the right wheel.
Right. It completely ignores the engine, the transmission, the fuel injection system, and, the actual driver.
So today, we are going to put a stake in that zombie. We're going to completely dismantle that old map and build a new one from the ground up.
I like the sound of that.
Because the reality of what is happening inside a creative brain is so much more complex, and frankly, it's so much cooler than just using the right side.
We are moving way beyond the metaphors today.
Yeah.
We are getting into the actual physical infrastructure,
Yeah.
the hardware and the software of the mind.
And we have a massive stack of research to get through. I mean, we are pulling from a whole dossier of paper spanning 20 years. We're going all the way back to the seminal white matter wars of 2010.
Oh, that was a very confusing time for the field. But it was absolutely crucial for understanding where we are now.
Then we're looking at the first real functional maps of improvisation. That's from around 2015. And we are going all the way up to a brand new groundbreaking study. This just came out in 2025 in JAMA Network Open.
And that 2025 paper is a real game changer. It identifies something they're calling a creativity circuit.
Mm-hmm.
And it really challenges our fundamental assumptions about how the brain manages novelty.
Because the mission for us today is to answer one single fundamental question. What actually changes in the brain when we create? Is it about having more brain power? Is it about connecting things better? Or, and this is where it gets really strange, is it actually about shutting certain parts of the brain down?
It is a bit of both, I think,
Yeah.
but not in the way you might think. To really get it, we have to stop looking at the brain as just this blob of jelly.
Right.
We have to start looking at it like a map of cities and highways connecting them.
Okay, let's unpack that. This is section 1 of our deep dive. The structural highway. Now, when we talk about brain structure in, movies or pop science, we always hear about gray matter. That's the star of the show, right? Poirot uses his little gray cells.
Right. Gray matter gets all the press. And for good reason. Gray matter is essentially the computing centers. Think of those as the cities on our map.
The processing hubs.
Exactly. That's where the neurons reside, where the cell bodies are, where the actual work of thinking happens. If you're doing a math problem or remembering a face or deciding what to eat for lunch, that work is happening in the gray matter.
But you can't have a functional country with just cities. You need roads. If New York can't talk to Los Angeles, nothing happened.
Precisely. And for a long time, neuroscience sort of ignored the roads. We call it white matter.
Okay.
These are the massive bundles of axons, these long nerve fibers that connect the cities. They're white because they are coated in this stuff called myelin, which is a fatty substance that acts like insulation on an electrical wire.
And that insulation is crucial for speed, right? It's about how fast the signal travels.
It's vital. I mean, the thicker the myelin sheath, the faster the signal travels down the axon. We're talking about the difference between an old dial-up connection and modern fiber optics.
Wow.
If you have poor myelination, the signal degrades or arrives late or it just gets lost. But if you have really robust white matter, the signal zips across the entire brain in milliseconds.
So scientists must have a way to measure the quality of these roads, these highways. In the papers we have here, they keep referring to a metric called FA, fractional anisotropy. That's a mouthful.
It is. It is a bit of jargon, but the concept is actually pretty intuitive when you break it down.
Okay.
Imagine a perfectly smooth, straight water hose. No leaks, no kinks, just a perfect tube.
Yeah.
If you turn on the tap, the water rushes through in one direction very fast, very efficiently. That's high fractional anisotropy, or high FA.
So the water is the information flow.
Exactly. In a brain scan, specifically something called diffusion tensor imaging, or DTI, we're not tracking information, but we're tracking the movement of water molecules. In a healthy axon, water can only really move up and down the fiber. It's constrained. That gives you a high FA value.
Okay, that makes sense.
Now, imagine a hose that's old and leaky. It's got holes in it. Maybe it's bulging in some spots. The lining is all rough. When you turn on the water, it sprays out the sides. It swirls around. It doesn't move efficiently from one end to the other.
That's low FA.
That's low FA. The water can diffuse in all directions. It's a less organized, less efficient flow.
So if I'm building a hypothesis here, just from logic,
Right.
you would have to assume that a creative genius, a Da Vinci or an Einstein, has the best highways in the world.
Right.
You'd expect high FA everywhere.
Oh.
Super efficient communication between all the cities. You want them talking as fast as possible.
That would be the logical assumption. Better brain equals better wiring.
Yeah.
It makes perfect intuitive sense. But this is where the data gets messy, and I think really fascinating. We have to look at what I like to call the Civil War of 2010. We have two major studies that came out in the same year looking at the same thing, the link between white matter and creativity, and they found, well, let's just look at them.
Okay, let's start with the first one. This is from Jung and his team, published in 2010. The title is White Matter, Integrity, Creativity, and Psychopathology, Disentangling Constructs with Diffusion Tensor Imaging.
Right. So Rex Young and his team used that DTI scanning to look at the white matter highways. They recruited a group of healthy young adults, and they measured their creativity using a composite creativity index.
What does that involve?
It's a bunch of different tests, things like divergent thinking tasks. So, how many uses can you think of for a brick?
The classic test.
The classic. Or they'd have them draw original designs from a set of simple shapes. They combine all these scores to get one big creativity number for each person.
Okay, standard stuff. And when they looked at the highways of the highly creative people, what did they find? Better wiring.
They found the exact opposite, an inverse relationship.
Inverse. You mean
Yeah.
worse highways meant more creativity? That can't be right.
Specifically, and this is important, in the left inferior frontal white matter. The lower the FA, the less organized the wiring, the leakier the hose, the higher that person's creativity score was.
That seems completely counterintuitive. I don't get it. Why would bad wiring make you more creative? Is the signal getting lost and stumbling into something new?
That's one way to think about it. This leads us to what's called the disinhibition theory. Imagine your brain has all these filters, and usually you want those filters to be really strong.
Sure.
When you're driving, you want to focus on the road, ignore the billboards, ignore the radio, ignore the squirrel that just ran by. You want to get the data from point A to point B without any distraction.
You want efficiency.
But Young and his colleagues argue that if the wiring in that specific frontal area is a little leaky or less efficient, it might actually allow unfiltered information to sort of collide. It slows down the processing just enough to let the side roads and the weird detours open up.
So it's allowing the weird ideas through? The noise is becoming part of the signal?
Exactly. It supports this idea in creativity research called blind variation. If you have a super efficient highway, you get from point A to point B perfectly every single time. That's great for doing your taxes or landing a plane.
Right.
But creativity is often about finding point C, which is off in the woods somewhere, not even on the map. Lower integrity in that specific spot might allow for that kind of mental wandering, that exploration.
And the title of the paper mentions psychopathology. That's a pretty heavy word to throw in there.
It is. Jung explicitly connects this to the continuum with psychopathology. We often see similar white matter patterns, lower integrity in these same frontal regions, in people who have, say, a proneness to psychosis or even schizophrenia.
Wow.
There's a difficulty in filtering out irrelevant information. For a patient, that could be overwhelming and terrifying. Everything feels deeply significant. For an artist, that same biological trait might be the source of their inspiration, seeing connections and patterns where everyone else just sees noise.
So creativity requires, or at least benefits from, a little bit of chaos in the wiring, a few potholes in the road to shake things up.
That was the big takeaway from Jung. It was a huge deal. But then, literally in the same year, we have this other study. It's from Takuchi, also the 2010. The title, White Matter Structures Associated with Creativity.
And let me guess, knowing how science works, they found the exact opposite.
Of course they did. Science is never that easy, is it?
Never.
Takuchi and his group found a positive relationship. They found that increased FA better wiring, the superhighways in the frontal lobes, the corpus callosum, and the temporal-parietal junction all correlated with higher scores on divergent thinking tests.
Okay, so this is a direct conflict. Jung says bad wiring in the left frontal lobe helps because it lowers inhibition. But Takuchi says good wiring across the whole front of the brain and especially in the corpus callosum helps. Who is right?
I think they both are. And this is the key to understanding the structural architecture of creativity. It's not one or the other. Takuchi's findings support what we call the integration theory.
Integration.
Right. Think about the corpus callosum. That's the massive bridge of white matter fibers connecting the left and right hemispheres of your brain.
It's the biggest highway of all.
By far. Takuchi is arguing that creativity requires taking a concept from the left hemisphere, maybe a word, a specific definition, a logical problem, and smashing it together with a visual or an abstract or a spatial concept from the right hemisphere.
You need a superhighway for that collision to happen. If the bridge is weak or slow, the ideas can't meet in the middle.
Precisely. If you can't shuttle data back and forth between distant brain regions quickly and efficiently, you can't make those surprising distant connections. So the creative brain isn't just better wired or worse wired.
It's a specific cocktail.
Exactly. It's a specific recipe. You want high-speed integration between hemispheres and distant lobes, which is what Takuchi found. But maybe, just maybe, you also want some lower integrity in the local filtering regions, like Xun found, to allow the crazy ideas to survive the trip in the first place.
That's a great analogy. It's like a city that has a super fast subway system connecting all the different boroughs. But the neighborhoods themselves are a little bit chaotic and interconnected in these messy, unpredictable ways.
That's a perfect way to put it. And this idea was synthesized a bit later in a 2017 study by Rex et al. Called Structural Correlates of Openness and Intellect. They made a really important distinction.
Okay.
With pure intelligence, like an IQ score, we almost always see that more is better. More brain volume, thicker cortex, better wiring across the board.
A bigger engine makes a faster car. You just want to compute, you want raw power.
Right. If you want to be a human calculator, you want high efficiency everywhere. But with creativity, Rex's group found that it's associated with both increases and decreases in cortical thickness and volume. It's a distinct structural signature.
So it's not just smart plus something else.
No, it's a different architecture entirely. An architecture that's built to balance raw efficiency with productive disinhibition.
So that's the hardware, the highways and the cities. We have this picture of a brain that it's built to be both fast and a little bit loose. But a computer is useless without software. We need to talk about how these parts actually talk to each other in real time. The software.
The functional networks.
This moves us into section 2, the dynamic duet. Now, for the longest time, I thought the brain had two basic modes, working and resting. You know, like I'm either doing my job or I'm on the couch zoning out.
And that was the prevailing view in neuroscience for decades. We mapped these two massive brain-wide networks that seemed to govern those two states. In one corner, you had the executive control network, or the ECN.
The ECN, who is that guy? What does he do?
That's your brain's CEO. The ECN lives mostly in the dorsolateral prefrontal cortex, the DLPFC. You'll hear that acronym a lot. This network turns on when you are solving a math problem, focusing on a spreadsheet, or trying to hold a phone number in your head.
The focused mind.
It is goal-oriented, it's focused on the external world, and it's all about control. It's the get things done network.
And in the other corner?
Who's its opponent?
In the other corner, you have the default mode network, the DMN.
The DMN.
This network includes areas like the medial prefrontal cortex and the posterior cingulate. For years, scientists thought this was just the brain's idle state. It turns on when you close your eyes, when you daydream, when you think about yourself or what you did yesterday or what you're having for dinner tonight.
The daydreamer.
Exactly. The daydreamer. And the core assumption, which was supported by a lot of data, was that these two were enemies. They're usually anti-correlated.
Meaning, when one is on, the other is off. When the CEO of the ECN walks into the room, the daydreamer, the DMN, stops talking. And when the daydreamer starts rambling, the CEO can't get any work done. You can't focus on a spreadsheet and daydream at the same time efficiently.
Right, until we looked at creative brains.
This brings us to a really pivotal paper. This is Beatty et al., 2016, published in Trends in Cognitive Sciences. The title is Creative Cognition and Brain Network Dynamics. And Roger Beatty is a name you're going to hear a lot in this stack. He's a real heavyweight in mapping these networks.
So what did Beatty find when he put creative people into the scanner and gave them a task? Did the CEO just take over?
He found something incredible. He found that in highly creative people, this antagonism, this rivalry, it just breaks down. During creative tasks, the default mode network and the executive control network actually start to cooperate.
So they stop fighting and start dancing together.
It's a dynamic duet. And if you think about the creative process, it actually makes perfect sense. First, you need to generate an idea, right?
Right, the spark.
That's the DMN. It's spontaneous, it's chaotic, it pulls from your deepest long-term memories without you even asking. It just throws paint at the wall. It's the network that says, what if clouds were made of marshmallows?
Okay, but if you only have the DMN, you're not being creative. You're just hallucinating or daydreaming. You're not solving a problem. You're just drifting.
You're just drifting, exactly. You need the editor. You need the CEO. You need the ECN to step in and say, okay, that idea is garbage, that one is illegal, but this one, this marshmallow cloud idea, this one has potential. The ECN evaluates, constrains, and refines the chaos that the DMN generates. It takes the marshmallow cloud and helps turn it into a Pixar movie.
So the aha moment isn't just one part of the brain lighting up. It's these two usually opposing networks finally shaking hands.
And holding that handshake is incredibly difficult for the brain, metabolically speaking. That's why true, deep creative work is so exhausting. You are forcing the brain to do something it doesn't naturally want to do. Keep the gas pedal and the brake pedal active at the exact same time.
That explains the creative hangover. I mean, after a deep session of writing or strategy, I feel physically depleted in a way that just answering 100 emails doesn't do to me.
It's a unique and very high cognitive load. But there's a missing piece here. If the CEO and the daydreamer are usually fighting, who's the referee? Who decides when it's time to switch from generate mode to evaluate mode? Who introduces them at the party?
Right. There needs to be a switch.
There does. And that brings us to the salience network. I'm looking at a paper from Sinowski and Popank 2019, published in Neuroimage. And they dive deep into this switching mechanism.
The salience network.
Right. The salience network is anchored in a part of the brain called the anterior insula. And you can think of it as a toggle switch. It's constantly monitoring the stream of consciousness coming from the DMN, and it decides what is salient or important enough to forward to the executive control network for more rigorous processing.
So in a highly creative person, the salience network is just really good at spotting the little flecks of gold in the giant stream of DMN garbage.
Ideally, yes. That's the idea. Sinowski and Popank found that the efficiency of this switching is crucial. If your salience network is lazy, you might have great ideas bubbling up from the DMN, but you never realize they're great, so the ECN never gets to work on them.
Or the opposite, right?
Or the opposite.
Yeah.
You might be too critical, with the ECN dominating, and you never let the weird ideas bubble up in the first place. The salience network facilitates that delicate shift from internal generation to external evaluation.
But Sinowski's paper found some other weird things, didn't they? They found predictors of creativity in parts of the brain I really didn't expect.
They did. They found that the cerebellum and the parahippocampal gyrus were surprisingly robust predictors of a person's creativity scores.
Wait, the cerebellum, isn't that for, like, balance and motor control? It's the thing that keeps me from falling over when I walk, right?
That's what we all learned in Biology 101 for sure. But the cerebellum is this incredibly dense structure. It contains more neurons than the rest of the brain combined. We now know it's involved in all sorts of complex modeling and automation of processes.
So what's it doing for creativity?
Sinowski suggests that the cerebellum might help automate the creative search process, making it smoother and more efficient. It helps turn the creative process from a clunky manual transmission into a seamless automatic.
So it's almost like developing muscle memory for creative thinking.
That's a great way to put it. It streamlines the search. And the parahippocampal gyrus. That's all about deep memory. It's involved in encoding and retrieving rich, detailed scenes and contexts. Its involvement suggests that creativity is deeply tied to how efficiently we can pull these rich, detailed files from our long-term memory archive. You can't remix a song you've never heard. You can't write a novel without a deep well of experiences. You need that memory access.
Oh, we have the highway, which is the structure. We have the dynamic duet, the DMN and ECN. And we have the switch, the salience network. But I want to talk about what it feels like. I want to talk about that magical moment where the editor disappears entirely. I want to talk about flow.
The holy grail of creativity.
And for that, we have a paper here specifically on musical improvisation. This is another one from Beatty, 2015, a review in Neuroscience and Biobehavioral Reviews.
Improvisation is the perfect natural laboratory to study this because it happens in real time. You can't go back and edit. If you're Miles Davis on stage, you are creating and executing simultaneously.
Yeah.
There is no eraser.
So they put jazz musicians in an fMRI scanner, which sounds like the worst gig ever, by the way. Here, lie perfectly still in this loud magnetic tube and be soulful.
It is definitely not the Village Vanguard, that's for sure.
Yeah.
But they did it, and they compared what the brain was doing when the musicians played a memorized piece like scales or a standard tune they knew by heart versus when they were asked to improvise over a backing track.
They wanted to see the difference between reproducing and creating.
Exactly.
And what happened, what lit up.
Well, when they improvised, they saw some of the expected stuff. Motor planning areas lit up because they're, moving their fingers on the keyboard or the trumpet. The pre-SMA and PMD were active, but the really fascinating finding, referencing earlier work by Lim and Braun in 2008, was what turned off.
The deactivation.
Yes.
Yeah.
They saw a significant large-scale deactivation of the DLPFC, the dorsolateral prefrontal cortex.
The CEO we just talked about. The hub of the executive control network.
The very same.
Wait, hold on a second. We just spent 10 minutes establishing that the breakthrough in understanding creativity is the handshake between the DMN and the ECN. Now you're telling me that to truly improvise, we have to kill the ECN. We have to fire the CEO.
That is the paradox.
Yeah.
And it seems to depend entirely on the type of creativity we're talking about.
Okay.
If you are solving a complex engineering problem or writing a poem where you are constantly revising as you go, you absolutely need that DMN-ECN coupling. You need the editor in the room.
Yeah.
But for rapid fire, real-time improvisation, you need to unclog the pipe. You need to shut the inner critic up.
So they literally stop judging themselves.
Biologically, yes. If your DLPFC is active while you're trying to play a solo, you're thinking, is this the right note? Does this sound stupid? Am I following the rules of the chord changes? By deactivating it, you allow the raw, unedited output of the generative networks, like the DMN, to flow directly into motor execution.
That's flow.
That is the neurobiological definition of the flow state. It's a state of hypofrontality, low frontal lobe activity. You are physically incapable of self-doubt in that moment because the part of your brain that generates that doubt is temporarily offline.
That makes so much sense, but does this happen to everyone? I mean, if I jump on a piano right now and just start banging on the keys, am I deactivating my DLPFC?
No.
Because it doesn't feel like flow, it feels like panic.
It probably feels like panic, and you're probably not deactivating it at all. You're likely thinking, I don't know where middle C is, everyone is looking at me, this sounds awful. That panic lights up your DLPFC like a Christmas tree. This is where expertise comes in. A study by Pino et al. In 2014 found that more experienced improvisers show less activity in these executive control regions than novices do.
So the expert brain is actually doing less work to be creative.
It's more efficient. It's automated. Pino found that while there was less metabolic burn in the control centers, there was actually higher connectivity between the frontal areas and the motor regions. The expert has built a structural and functional highway that allows them to bypass that conscious checkpoint.
They've trained the editor to step out for a coffee break when it's showtime.
That's it. That's why trying harder often kills creativity. When you consciously try, you are forcefully re-engaging the executive control network. You're re-engaging the DLPFC right when you need it to step aside.
It's like trying to manually breathe. The second you think about it, it becomes awkward and forced.
Perfectly put.
Okay, this is all fascinating. The balance of networks, the flow state. But now we need to jump to the future, or I guess the present, since we're in 2026. I want to talk about the paper that just came out last year. This is Kucha et al., 2025, in J-Man Network Open.
This is a massive study. This isn't just 20 jazz musicians in a tube. This is a huge meta-analysis using a technique called coordinate network mapping.
What does that mean in plain English?
It means they didn't just run one new experiment. They took the data from hundreds of previous studies, so thousands of people, thousands of specific brain activation coordinates, and they fed it all into a massive computer model and asked one question. Is there a single common brain circuit that explains all of this? Is there a universal map for creativity?
Is there?
They found one. But it wasn't a region that turns on, which is what everyone expected. This is the big twist. The specific universal signature of the creativity circuit is defined by negative functional connectivity to the right frontal pole.
The right frontal pole. Okay, let's call it the RFP. Let's locate that. Where is it in my head?
It's right behind your forehead, on the right side. It's the most anterior, the most forward part of your entire brain. It's evolutionarily one of the newest parts of the cortex.
And then you said negative connectivity. That means when the creativity network is firing on all cylinders, this spot needs to be
silent. Or, more accurately, anti-correlated. It needs to be out of the loop. Its influence needs to be actively suppressed.
So what does the right frontal pole normally do? Why do we need to shut it up to be creative?
Well, the right frontal pole is thought to be the kind of high-level sensor. It constrains novelty seeking. It's the part of your brain that says, stick to what you know. Stick to the safe path. Don't eat that weird berry you've never seen before. Don't walk into that dark cave.
It's the ultimate buzzkill. It's the brain's safety first officer.
And in an evolutionary sense, it's an incredibly important survival mechanism. You don't want to be too creative when you're running from a lion. You want predictable, safe, learned behavior.
Sure.
But to be creative, you have to inhibit that inhibitor. You have to find a way to turn off the brain's no button.
And Cooch's paper didn't just look at healthy brains, right? They went a step further and looked at patients with brain damage. This is where this study gets really poignant and, frankly, kind of shocking.
This is the most shocking part of the paper, I think. They looked at patients with lesions, so damage from strokes or injury to different parts of the brain. And they found that patients with damage specifically to the right frontal pole often showed increased creativity after their injury.
Increased. You damage a part of the brain and you get more creative.
It's a phenomenon called paradoxical functional facilitation.
That is a great term. Paradoxical facilitation. Breaking it actually makes it work better.
And it connects to something we've seen in clinical neurology for a while. It connects to patients with a specific type of dementia called frontotemporal dementia. It's a tragic disease, but there's a variant where the atrophy, the brain decay, starts in these frontal lobes, specifically in these inhibitory areas. There are dozens of documented cases of patients, accountants, stockbrokers, engineers, people who never showed any artistic inclination, who, as the disease eats away at their frontal lobe, they suddenly start producing this obsessive, detailed, sometimes beautiful art.
Because the sensor has died.
The sensor is gone. The dam breaks.
Right.
All that raw sensory data, all those wild associations that the right frontal pole used to suppress, they just pour out completely unedited. The 2025 paper confirms with large-scale data that creativity isn't just about adding activity. It is strictly tied to subtracting the influence of the right frontal pole.
This connects all the way back to the Jung study from 2010 we started with, the disinhibition theory.
It's full circle. It's incredible. Jung saw it in the structure of the white matter. Lower integrity meant less efficient filtering. Cooch and his team see it in the functional circuit. You need to functionally disconnect the right frontal pole to let the new ideas in. Whether that disconnection happens because of a flow state or a particular white matter structure, or sadly because of brain damage. The core mechanism is the same, subtraction.
So if we step back and try to summarize this entire mechanism, we have a pretty clear recipe now. I'm looking at the summary from another Beatty paper from 2018, Neuroscience of Creativity. He breaks it all down into 3 specific cognitive mechanisms that map onto these networks we've been talking about. Let's just run through them.
Sure. This is the playbook.
Okay. Mechanism number 1, goal-directed memory retrieval.
That's the DMN and the ECN working together. That's the handshake. You have a goal, which is the ECN. I need a solution to this marketing problem.
Yeah.
And you are actively digging into the archives of your mind, the DMN, to find the raw materials. It's an active search, not just waiting for lightning to strike.
Got it. Mechanism number 2, prepotent response inhibition.
That's the ECN, again, acting as a gatekeeper. A prepotent response is just science speak for the obvious answer, the cliche. If I say salt, you immediately think pepper. That's a prepotent response. Your brain is wired to give the easiest, most common answer to save energy. To be creative, you have to actively inhibit the word pepper. So you can think of lake or wound or earth. You have to stop the automatic association to find the novel one.
And finally, mechanism number 3, internally focused attention.
This involves the coupling between the ECN and the visual network, but essentially it's about blinding yourself to the outside world so you can build and manipulate mental images. You have to ignore the sensory input of the room you're in, the humming of the fridge, the light from the window, to really see the idea in your head.
And Beatty's claim in this paper is that this network signature, this whole playbook, is so distinct that they can now predict how creative you are just by scanning your resting brain.
That's the creative predictor. It's mind-blowing. They don't even need you to do a creative task. They can just put you in the scanner and look at how your DMN, ECN, and salience network are talking to each other while you're just lying there doing nothing. If that high creative network is strong, if those highways are already paved and the handshake between the networks is tight at baseline, they can predict your divergent thinking score with a pretty high degree of accuracy.
That is wild. It suggests that creativity is, to some extent, a default setting for some brains. It's how they're wired at rest.
That suggests it's a trait, yes.
Yeah.
But we have to remember, the brain is plastic. Connectivity can change with training. We know that improvisation training, for example, measurably changes the connectivity in these networks. You can pave your own highways.
So let's bring this all together for a final summary. We've moved from these simplistic right brain myths to a really complex and, I think, beautiful reality.
We really have.
Structurally, the creative brain is a mix. You need some high-integrity superhighways for integration connecting the left and right hemispheres, just like Takuchi showed us. But you also seem to benefit from some lower integrity, maybe leakier zones in the frontal lobe for disinhibition, which is what Jung argued.
Correct. It's a mix of superhighways and winding dirt roads.
And then, functionally, it's this incredible cooperation, this dynamic duet between the daydreamer, the DMN, and the editor, the ECN. And that dance is mediated by the swish, the salience network.
Yes, it's dynamic duet.
And the master key, the one thing that might just unlock the whole system, seems to be this tiny spot at the front of your head, the right frontal pole. When that guy is quiet, whether that's through a flow state or meditation or even, bizarrely, through injury creativity blooms.
That really does seem to be the crucial finding of the last decade. Creativity is as much about subtraction as it is about addition. It's the subtraction of inhibition.
Which raises a very provocative question to end on. If the right frontal pole is a creativity damper, and we know exactly where it is.
Uh-oh. I know where you're going with this.
Could we?
Okay.
Could we just turn it off? I mean, we have technologies like transcranial magnetic stimulation, TMS. We can inhibit specific brain regions non-invasively with magnets. Are we on the verge of on-demand creativity? Could I put on a helmet, get a zap to my right frontal pole, and suddenly paint like Picasso?
Theoretically, it's plausible. There have been some famous studies. Alan Snyder in Australia did some of this work, using TMS to inhibit the left anterior temporal lobe. And they found temporary bursts of insight and savant-like drawing skills in normal people. Targeting the right frontal pole, based on the Kuchit 2025 data, is the next logical and very tempting step.
But there's always a but.
There's a huge but. Remember, the RFP is there for a very good reason. It keeps you safe. It keeps you socialized. It's the thing that stops you from saying that brutally honest but terrible thing you were thinking at a dinner party. It keeps you from making ridiculously risky financial bets.
So you might paint a masterpiece, but you might also make some very questionable life choices while you're doing it. You might lose the filter that keeps you employed.
Exactly. You might lose the filter that keeps you.
Well,
that keeps you sane.
high risk, high reward, just like creativity itself.
Precisely.
We're going to leave you with that thought. Nurture your own DMN-ECN handshake. Give yourself time to daydream, but don't forget to invite the editor back into the room to finish the job. And maybe, just maybe, try to tell that right frontal pole to quiet down every once in a while. Thanks for listening to The Deep Dive.
Stay curious.